Welcome, everybody. I can tell from the list of registrants today that we have a number of folks that are maybe new to Webinar Wednesday that haven't been with us before. So if you are new to us, as Melissa mentioned, welcome. And to those of you who have been here before, welcome back. We have just a great topic for you here this afternoon on this whole idea of artificial intelligence. I'd like to start with this thing that I found in a book, actually. When we talk about what is AI, when we talk about what is artificial intelligence, I found this in a book not too long ago, and they asked the question, what is opinion, size, age, shape, color, origin, material, purpose? That is the question. I want everybody to think for a moment about what that is. What is opinion, age, shape, color, origin, material, purpose? And the answer to that question is that is the order in which you, without even knowing it, place adjectives before a noun. We don't even realize that we do this, but this is the reason that if I say lovely little old rectangular green French silver whittling knife, it sounds a little weird, but you know exactly what I'm thinking about. You can kind of picture what that is. If I say old little French whittling lovely silver rectangular green knife, I sound like I'm crazy. It's why we can't say my Greek fat big wedding or my walking leather brown boots or green little men. Again, we do this without even knowing it. That's the order in which we place adjectives before a noun. Here's another question for you. What is IAO? IAO is the order in which you put similar sounding words based upon their vowels. So that's why it's really hard for me to say mash, mish, chat, chit, dally, dilly, shally, shilly, top tip, hop, hip, flop, flip, tack, tick, and dong, ding. But I can say mishmash, chit, chat, dilly, dally, shilly, shilly, tip, top, hip, hop, flip, flop, tick, tack, and ding, dong really easy. There again, we do this without even realizing that we do it. And when we think about this, when we think about the intricacies of the human mind and the way that we think, we start to realize what a challenge that people like our guests today have in making machines think like human beings, because the way we always think and make decisions isn't always necessarily all that logical. And so now I want you to think about Waymo. And I want you to think, if you're not familiar with Waymo, Waymo is Google's self-driving cars. So these are the fleet of self-driving cars that Waymo has. And this was an article, as you can see from the date, this is now three and a half years ago. They had reached 4 million self-driven miles with their cars. And I read this article and I got a little bit interested in this. I have a friend of mine at a technical college in the Midwest that got me hooked on this whole idea of these self-driving cars and how many miles they're driving. So that was November of 2017. Not too long after that, they reached 7 million test miles. By July 20th of 2018, they had driven 8 million miles on public roads. If we turn the clock forward to the beginning of 2020, 20 million miles on public roads was what those autonomous vehicles had been driving. And after that, Google must have stopped reporting it because I haven't seen an update. But 20 million miles on public roads is how many miles those vehicles have driven. Now, I want you to think about this. It is not just the actual miles that self-driving cars are driving on actual roads. What's even more important are the literally billions and billions, billions and billions of simulated miles that vehicles are driving, doing 100 years of driving per day, according to this article, while COVID was going on. And here is why this matters, and here's why it's pertinent to today's discussion. If we think about all these vehicles, every single one of those Waymo cars is gathering all kinds of information and sending it up to the cloud. What are the traffic signs that it's seeing? Is something sitting next to the road a mailbox, or is it a person? How fast is it driving? How fast are other cars driving? Gathering all of that information and sending it up to the cloud. And from there, it's analyzed, and all of that information goes down to every single other Google car. 20 million miles of driving experience then of all of these Google cars. And to put that into perspective, by the way, 20 million miles, the average human being drives about 13,500 miles a year, at least in the USA. So if you think about 20 million miles of driving experience, that's 1,500 years of driving experience. And so we take all of that data that coming from every single one of those vehicles and send it back up to the cloud. And that from the cloud, it goes back down to every single individual car. And over time, every car is as smart as all of the cars put together. And that is part of what is revolutionizing our world using artificial intelligence and machine learning, the topic that we'll be talking about today. So, one really quick application, as many of you know, I spent my career in manufacturing. Not too long ago, I saw this exhibit and I saw it was a paint robot that was painting motorcycle tanks, painting the fuel tanks from motorcycles. And it was kind of a fascinating thing. And I stood there and I watched it for a while. And then an engineer walked over to me and he said, "You know what? If you think that's cool," he said, "check this out." And we walked across the hall and there was a digital twin, a complete replica of that process that was running digitally. And here's why that's important. And here's how artificial intelligence plays into that model. When we have a digital twin, we take first that physical manifestation of our process and we load it up with smart sensors and smart devices that are gathering all kinds of data in real time. And we take that information and we send it to the digital twin. And the digital twin gets smarter and smarter and smarter and gets closer and closer to the actual process. And then when we want to make a change to that process, we don't change the actual process on the shop floor. We first go to the digital twin and we change it there and we experiment with it there. And not until it's working exactly the way that we want it to do we take it back to the floor. Another really, really fascinating application of artificial intelligence. So I've been fascinated by this topic for a long time. I know from our registrations how many of you are also totally fascinated by this topic. And that's why it's such a pleasure for me to introduce our guests that are with us today. The first introduction is my friend Paul Karam. Paul is the director of engineering for Quanser. Now, he has run their engineering operations for 10 some years. So he's been doing that for at least 10 years. Prior to that, he was managing their industrial projects and robotics technology. He did that for 6 years. He graduated with honors from Canada's University of Waterloo. So we're so excited to have Paul with us today. We're also excited to welcome to Webinar Wednesday, Murtaza Bora. Now, Murtaza has a fascinating background as well. He's an R&D engineer at Quanser, where he develops software and control architecture for autonomous vehicles and robotic systems. He has tons of education experience as well, and he has mentored secondary students. He has mentored graduate students. He has mentored undergraduate students, tremendous amounts of experience in the world of education. He has a bachelor's degree in applied science in aerospace engineering from the University of Toronto. And get this, I didn't even know this degree existed, but it sounds really, really cool. He has a master's degree in space mechatronics and mobile robotics from the University of Toronto's Institute for Aerospace Studies. So, Murtaza and Paul, it is so awesome to have you here. You guys are absolutely subject matter experts in this area. I know our audience is going to learn so very much from you. And I'm going to begin with a question for Paul Karam. Paul, can you share with our audience, where do you see artificial intelligence being employed or deployed in industry right now?
All right. Well, thank you, Matt, and thank you, Melissa, for inviting us today to Webinar Wednesdays, and hoping this is our first and not our last time on the show. So, thank you for hosting us. And yeah, definitely, this is a very interesting topic. So, for those of you on the audience that might not know us, so our company is called Quanser. We work very closely with Matt and the rest of the team at Lab Midwest, and Quanser is comes from two words put together, amalgamation of two words of question and answer. And that is because we live and breathe education. We live and breathe academic research, and we are an academically focused company that brings, cutting edge trends and these exciting, things like AI, machine learning, mechatronics, robotics, unmanned systems, self-driving cars, and we make them academically accessible for varying age groups in education settings. So for today's talk, we want to really help all of you come to grips and try to figure out how do you actually start introducing concepts in artificial intelligence in your classes, be that if it's in high school, college, undergrad education, all the way to graduate and research. a lot of you, and I'm sure you're not finding out here for the first time. AI is everywhere now. Everywhere, every website you visit likely has some AI metric of bucketing who you are, what kind of person you are. Amazon knows exactly what you're about to order before you even order it. All the photos that you have in the cloud already have tags of who the people are, and you can, for me, I can just search my kids, and magically every single picture I've ever taken of my kids from the time they were born till now show up. So AI is everywhere. AI is is being instrumented in many places. So it is overwhelming, and definitely we can see that. So our perspective when it comes to artificial intelligence and sort of these new autonomous and intelligent smart systems is what Quanser always does. What we try to do is to develop solutions that provide you as the educator or you as the researcher and a platform to deploy the academically appropriate concepts to your students. And how are we going to do that? So if we go to the next slide, I'll just give you a quick example of what Quanser does in general and how this really pertains for the subject of AI. So here what you have, this is happening in my basement now since we've had to move our labs into our homes. We have our self-driving car research studio, and this is a research studio for graduate research. So it's an open architecture, highly performant car that has many sensors and has the computing power to do a lot of great things when it comes to all things self-driving car. But what we've done in our paradigm to expose this is we've made this car capable as a hardware platform to actually deploy and realize artificial intelligent algorithms, artificial intelligent processes. And so what my colleague Murtaza will show is exactly how we're going to take advantage of some of the instrumentation on the car, some of the computing power on the car and elsewhere to really bring some of those AI concepts to life. So what you're seeing just simply here, there is no true artificial intelligence happening here, but it's quite intelligent in its own right, in the sense that it is mapping the room based on a lidar sensor only and being able to calculate its location every single time it gets an updated lidar scan, and based on the previous scan it can figure out how far it's gone and where it's turned as well. So this is just maybe it's not artificial, or it's getting to artificial intelligence right now, but what we want to show you is just how capable some of these systems are to really deploy artificial intelligence, and to be able to really understand and see artificial intelligence be put into practice on modern engineering systems.
Fantastic. Thank you, Paul. And I think the key words there are really how do we bring AI to life? And I know that that is such an important thing that the Quanser's doing, and such so important to our audience as well. Murtaza, turning our sights to you for just a moment. Paul talked about AI applications in industry. As you look at AI in the work that you're doing, how would you define artificial intelligence for our audience?
Thanks for having us, Matt. We see intelligence as really a collection of two high-level ideas. You've got experience and learning, and so experience is not just the collection of multiple ideas together, but it's also the connections or linkages between those ideas. And this allows you to put pieces of information together to make inferences collectively. And then you've got learning, which is the process of increasing your overall knowledge and connections, which is your experience. And this allows you to improve the ability to rely on that experience when needed, especially in new situations. Artificial intelligence then is the mathematical representation and algorithmic implementation of intelligence, a collection of data structures that can represent that experience and methods by which you expand and improve that experience. That's how we see it.
Fantastic. And moving right into, as you and I were chatting about this topic, you introduced me to some new terms, Murtaza, terms like supervised and reinforcement and unsupervised learning. Can you help our audience understand for the moment what those terms mean and how they fit into the overall field of AI?
Right. So these different terms, supervised, unsupervised, which sound complementary, and reinforcement, these are different learning methods that sort of depends on the problem at hand. And so in supervised learning, we let our system know the answer to the problem, but not why that answer is correct or how it should arrive at that answer. The AI improves its experience by making its own connections based on the problem at hand and the answer. So if you go to the next slide, in the example, you'll be able to see the depth images and RGB images captured from the Quanser QCar platform as it drives on our 1/10th scale track at our office. On the left side, you have manual driving, and we are collecting the images and steering commands from the driver. And then we pass that to an AI system that learns to replicate the behavior. On the right, you see the AI system driving the car autonomously based on the right answers we gave it. In reinforcement learning, we don't quite give answers to the AI system, but we give it rewards for taking actions that are favorable to us. So in this example, you have a Cube Servo 2 agent learning how to swing up and balance a pendulum over multiple cycles. The leftmost video shows you it just sort of starting to understand the behavior of the system. But as you progress right, you can see it's learning a balancing the pendulum is an action that gives me a lot of rewards, and it learns how to do that effectively. And then lastly, you have unsupervised learning. We provide data to the AI system and it can group or categorize that data or make inferences on that information, but there is no real right answer. So if you give 1,000 images of different cars to an AI system that's using unsupervised learning, it might come back and say, look, this is how I categorize them. And you might realize, oh, look, it did it by color, or it could do it by shape or by brand. But it's sort of a very interesting categorization tool.
Fantastic, and I can't tell you how fascinating this demonstration is to me. Both the one that you did certainly on supervised learning, talking a little bit about reinforcement learning, which is fascinating, and then into the unsupervised field. Now we're moving into a couple more definitions that I know that our audience is interested to learn about. What can you tell us about transfer learning, and how do we apply transfer learning?
Yeah, so this is something that engineers typically find very useful. Consider AlexNet. It's an AI system that's already trained. It can classify about 1,000 different objects. So here you can see it picks up my dog as a llama first and then a samoyed. And it's looking at all different objects in my office. And AlexNet is pretty good at doing this. It can pick up monitors, fruits, dogs, mice. It can differentiate colors, contours like CS0 shapes, triangles, circles, etc. But when you have AlexNet predict something, let's say it says there's something's a television, it makes that inference based on different ideas that it puts together. It might say, look, this object is rectangular, it has a black border, it has brightly colored pixels inside, it must be a television. And so if you look at me pointing my camera at the window, the same three information pieces sort of apply, and it thinks my window is a monitor as well, right? But if I want AlexNet to now learn new objects that I am interested in, and so that would be the next example, I don't have to sort of train AlexNet from scratch. What I can say is, well, take your existing experience and just develop new connections. So here we gave AlexNet about 10,000 images of our different Quanser products, and you can see it has picked up the QArm, the QCar, which are both sitting in my office. But then I didn't have some of our other products, which are virtual. So I ended up using the virtual ones. And Quanser Interactive Labs, which gives you multiple digital twins to work with, it can sort of identify them very well as well. So it picks up a Cube Servo and QBot right there. And so that's what transfer learning does. It gives you the strength to take existing AI technology and apply it to your immediate problem. In the next example, we again show you how to use transfer learning for something more practical. We wanted to learn how to detect road signs. And so you have an application here running in Simulink, and it's actually running on our QCar platform directly. And this is using the Intel RealSense camera. It captures an RGB image and then sends that over to my PC, which is acting like the cloud. And it does classification using MATLAB's deep learning toolbox. And so it can identify blank, which is there's no sign, a stop sign, a yield, and so forth. And then it sends that information back to the car. But again, this doesn't have to happen on my PC. This can directly happen on the car. It has an Nvidia Jetson TX2 on it. And so that allows you to directly do inference on the car.
Which is a perfect segue, Murtaza, into a question that we had for Paul. and that is we know Nvidia is doing some really, really interesting things in the artificial intelligence space. What can you share with our audience about what they're up to?
Yeah, so hopefully with all those great examples that Murtaza was showing really highlight the various directions anybody can go with AI. Again, AI is somewhat overwhelming and can go in different directions. And as Quanser, really focus on applied AI or actually distributed or implemented AI. The Nvidia technologies really come into the picture. So what Murtaza was showing there, for example, we had our Q car, which is an embedded system, and it's a mobile robot driving around. And Nvidia has done a lot to get themselves to be sort of the leading supplier when it comes to a lot of the self-driving. Technologies. So you can see there they have the Pegasus, which is intended to go inside a real vehicle. What we've done is we've taken that Jetson TX2 on the bottom left quadrant there, and we built a computer around it and put that on our Q car. So you already have an NVIDIA based processor. And what the NVIDIA has always been known for is their GPU technology. And it just, it so happens over the last decade that parallel processing and leveraging GPUs wasn't just great for graphics and gaming, but a fantastic processor architecture for deploying artificial intelligence. And so because NVIDIA has, had that technology and is now going towards leveraging that technology to things like AI, we've sort of adopted this paradigm across the board. So our car and our mobile devices are going to have NVIDIA based processors, in this case the TX2. And the other part where that we've also taken advantage of is we have as part of our solution what we call the ground control station. Basically that's functioning as your research cloud, and that's where a lot of the classification that Murtaza had showed as well was being done. So the car does some processing on itself, sends that information over to the cloud, where it takes advantage of an even more performant and a higher capacity GPU, classifies it based on the training and learning that Murtaza had implemented, and sends the classification back to the car, so the car knows, oh, there's a stop sign, here's my yield sign, and so on and so forth. So and this is just one implementation of this algorithm. As we develop self-driving cars with hundred thousands and millions of miles of real world driving plus simulated driving, these are the types of questions and technologies and architectures we need to be developing and really testing and researching what works better and how do you build robustness, reliability, and so on and so forth. So the fact that Nvidia has always been at the forefront of GPU technology, and over the last decade specifically, they've directed that over and above, gaming and graphics, and into the world of artificial intelligence and even more specifically self-driving cars. We're partnering with them in a great way to really take advantage of their hardware capabilities. And what Murtaza is going to showcase now is not just the hardware side, as powerful and performant the hardware is, that software architecture is equally as powerful as well.
Absolutely. So it's just, it's interesting as we think about how companies need to continue to evolve. What a great story of how a company like NVIDIA took existing technology, new technology, evolved into a new world of artificial intelligence and into a new space. And to your point, fascinating things going on the hardware side. And now, Murtaza, tell us a little bit about what software platforms you're seeing executed and deployed to implement artificial intelligence.
Yeah, there are quite a few different software tools available for setup, training, and deployment. You've got C++, Python, and MATLAB. These are strong programming languages that allow you to develop code, but then you don't have to write code from scratch. You've got application frameworks such as TensorFlow or PyTorch, or even the deep learning toolbox in MATLAB that allows you to rapidly develop applications. But training and deployment can be computationally intensive. And so you also need to use GPUs. And then GPU accelerated libraries like CUDNN and TensorRT allow you to do this computationally intensive task much faster. So once you have powerful GPUs, let's say in PCs, you can easily use CUDNN libraries TensorRT is favorable towards embedded computers that have limited resources to begin with. But there is another option for embedded targets. You can always acquire information on the target and then send it up to the cloud. Your AI system could entirely live and predict in the cloud and send results back. So Amazon Web Services, Google Cloud, both have solutions for this. So to sort of show you what this example looks like, you can see the Quanser Q-car platform driving autonomously in the next slide.
Absolutely.
Using
Go ahead.
Yeah, it's using some basic lane keeping algorithm.
Fantastic. And just to cue that up a little bit, you know, Paul, one of the things that I'm traveling all over the state of Michigan this week. That happens to be what I'm doing this particular week, meeting with
Right.
educators, meeting with educators at the university level, meeting with folks at the community college level, and so on. And I can tell you that everything we're hearing is all about applying this technology, about, you know, helping people learn it, helping students learn it in a way that applies to their everyday life that they can wrap their brain around. One of the things that I've been so very impressed about with regard to our relationship with Quanser is just number one, how incredibly brilliant all your people are. And I've told you that 100 times, but how great you are at taking really complex technology and putting it at a level where students at really every grade level, and we're teaching it in different ways at different levels, but you know, all the way into K-12 and all the way to complex, you know, graduate research programs, the applications of this technology and what you're doing is really fascinating. So if you would tell our audience a little bit about what you're doing there.
Yeah, perfect. So as you know quite well, Matt, we're working with you guys with Lab Midwest very closely with an opportunity in Michigan, and this is a fairly new endeavor for Quanser in the sense that we are taking this, you know, all this great research grade technology, and we're going to wrap it in a concept that is age appropriate. So in this case, you know, the way I'm describing what this is the beginnings of what you're seeing here, but essentially we're putting together an interactive museum exhibit, and this will be in a trailer that will be driven from school to school. In this case, the typical audience level is going to be grade 6 kids, and these are kids that some might be you know, become engineers and become developers and leaders in self-driving technologies, but most of them are just interested in knowing what it is, and you know, the earlier you educate them, the less fearful they might be of an autonomous car in the future, or something along those lines. And so our challenge to us in with this project is, how do we distill these great concepts and these really challenging, you know, engineering algorithms to in such a way to really highlight you know, to the kids what is happening there. And so we've sort of broken it down to 4 elements of sense, think, do, and talk, and those 4 elements are going to be highlighted. So we sort of distilled down all of those concepts into saying, hey, this is how the car sees. You can see on the left side there, it's seeing, you know, an RGB feed, and then it's doing some processing and thinking so that it can only extract the color that it wants. We're going to have 4 cars all navigating these paths simultaneously, so there's going to be a lot of talking, a lot of communication back and forth. There's going to be like Murtaza was showing, neural networks being deployed to analyze and classify different signs and so on. So, you know, we want to really show that, you know, when it sees a sign, this is what's happening. This is how it's running it against the, you know, the neural network that was trained. Or if it sees a road, here is how it's you know, taking it and extracting just the useful information with some images that we show over there. And so, you know, we're not we're halfway through that project as we speak, but this is a great way for us to really provide these exciting technologies, albeit quite complicated at some level. But you know, the challenge is, how do we distill them and make them age appropriate and accessible, really, to the audience, and in this case, just grade 6 kids. So looking forward to launching that project as well.
Absolutely. And who would have guessed just a few short years ago that we would be using the term neural network and sixth grader in the same
Yes,
conversation? It's
that's right, exactly.
absolutely fantastic. And really credit, Paul, to you and to your team for not just the concept, but how quickly you're moving on the development. It's really, really amazing to be partnered with you on this project. And I know our audience has got to be absolutely fascinated by this as well. Speaking of our audience, Melissa, I've got to believe we've had some interesting questions come through on the chat box since we've been on. And in the interest of keeping things moving along, and we always like to keep these around, 35 minutes or so. What do we have coming from the audience in terms of things that they'd like to learn from Paul and from Murtaza?
Thanks, Matt. And I'll just throw out that reminder, if you do have a question, now's the time to ask it. First question, I think, Murtaza, if you can answer this one. The individual asks, is there a particular programming language you recommend I start with?
It depends on your comfort level. So personally, I would go with either MATLAB or Python. Both of these are not low-level languages. They are high-level languages. And so coupled with TensorFlow, as well as the deep learning toolbox, they give you a lot of examples and application libraries to rely on to start developing instead of writing code from scratch. So that's what I would recommend.
Great, thank you. This one I'll pose to any of the panelists who feel comfortable asking. Have you noticed hardware manufacturers integrating AI into their platforms? For example, Rockwell Automation has created an AI module for their PLCs.
I mean, I can attempt to take this one. So thanks, Tom. That's a really good question. I think you're going to see a lot of hardware manufacturers across the board, regardless of the industry they're in trying to catch up to a certain sense, but also allow their users and customers to deploy things like classification, things like identification and sorting out unmodeled data, making sense of the data and things like that. And when you enable the hardware to take care of it, then that's when you get a lot more performance, as opposed to having to send it off to a cloud, or in some cases you might not have that connectivity. And so I'm not surprised that they're doing that. And really, I think what's happening behind the scenes or under the hood is that these suppliers are basically leveraging parallel computing, and in this, for example, with Nvidia, with their GPU technologies, that kind of paradigm where they're having parallel computing available as part of the hardware offering, so that you could deploy some of these software tools that Murtaza was talking about fairly rapidly, and that has a place to run on in this case, that AI module on the PLC, for example.
Great, thanks, Paul. I think we have time for one more question. And again, I'll just throw this out there for anyone. In an academic setting, what sorts of programs would we see something like the Quanser self-driving car studio being taught in?
I'm happy to take that one, unless Paul or Murtaza, you want to tackle it. But
go for it, Matt.
No, absolutely. I think the beauty of what Paul and Murtaza have shown us is literally we can go all the way into the upper levels of middle school and all the way through high-end research programs. And so I know that kind of working backwards through that continuum, Quanser's done amazing work on putting together in partnership with research universities, grant applications and funding models to fund advanced research in artificial intelligence. And so we can start all the way on that end of the spectrum. And if we have educators on that have interest in that type of a partnership, I know that we're certainly eager to have that discussion. And so we can certainly teach it at that level, but we're also seeing it in undergraduate and graduate programs. And so it can be anywhere from computer science, electrical engineering. We're even seeing it a little bit in manufacturing engineering, a little bit in mechanical engineering. So a wide variety of engineering applications. We have a number of community and technical colleges that are now going deep into Industry 4.0. Some call it IIoT, some call it advanced manufacturing technology. But this research and these learning opportunities have a home for certain in the community college. And as Paul articulated very well just a little while ago, in our high schools and our middle schools as well. So we see it across across those spectrums. And Paul, if I missed any, or Murtaza, go ahead and fill in the blank. But how do we do?
I think you
Yeah,
nailed it, Matt. Yeah, I think again, just our typically our solutions have always been at that higher ed, undergraduate engineering and research level. But as we start working with more and more of customers and colleagues that want to introduce these concepts at different levels, then it is more challenging to make things age appropriate. But I think it's on us to make sure we do that, because this is just this technology is in its infancy, and the more we can do to bring it to an age appropriate level, I think everyone will benefit from being introduced to it.
Absolutely. Thanks, guys. Matt, I'll leave it to you to wrap up.
All right. Well, thank you, Melissa. First of all, my thanks to both Murtaza and to Paul for just being incredible, incredible guests. We get to work with lots and lots of smart people here on Webinar Wednesday, and these guys are the absolute cream of the crop. Absolutely brilliant people, as you can tell from the presentation today. So thank you so much for being with us on Webinar Wednesday. Coming up next week, we will be spending some time with the CEO of the Milwaukee Tech Hub, as she is turning the city of Milwaukee into a destination for technical talent and for technology talent. And so doesn't matter where you live on the planet, if you have an interest in creating a magnet for technical talent, for technology companies, there are going to be some best practices shared next week that will be absolutely perfect for you and for anybody who has an interest in public policy and has an interest in technology. So with that, we're going to wrap up our time here on Webinar Wednesday. Again, thank you to our guests. Thank you so much to our audience for being with us today, and we will see you again next week.